Hello, everyone, and welcome to this week's Zoom for Thought. Today, we'll be having the tertiary talk of the quarter given by Max Johnson, who will tell us about secondary operations in algebra and topology, and I'll be the primary person to tell you that I'm excited. Take it away, Max.
All right, thank you so much. Just a quick disclaimer, I am a little bit under the weather, so if my voice sounds a bit raspy, I apologize, but I don't think it will make a significant difference. Okay, so a general outline of today's talk, I'm going to start by giving some motivation, and then I'm going to define and spend most of the talk talking about a secondary operation in algebra called the Massey product. And then assuming there's time at the end, which there should be, I will define the tota bracket in topology, give you some reason to believe they should be related, and then assert that they are. And then if there's still some time at the end, there are some like open problems and further directions that I might say a few words about. Okay. Conventions and disclaimers. The first is that while I was writing this, I didn't want to think about plus or minus signs, so I've decided to work over Z2. The second is that I didn't want to think about what assumptions I needed on my spaces. So if they need to be connected or CW complexes, just assume that I said that. The third is that I might change my gradings up without realizing it. I think I've got everything under control at this point in the talk after revising it. But if I ever start talking about like homological grading, feel free to ask me for clarification, or feel free to assume that it won't be important in the grand scheme of things. And then, of course, all exercises, if you're taking this for a grade, will be due by tomorrow midnight. So just a heads up for that. Okay, so motivation. So my first motivation, and all of the three that I'm going to present to you, are about how the cup product can give you more information about a space without actually adding anything to like cohomology's definition. And what I mean by that is when you define the cup product, you already have the same singular cochains, you already have the same cohomology groups, and yet you somehow dig a little deeper and get extra information without like asking the space for anything new, right? And so this allows you to say, distinguish the two spaces on my screen, the first of which is supposed to be a sphere with two little circles attached to it. And the second is supposed to be a torus. And this is a really classical example where if you take, I'll draw it out. If you take a generator here on the torus, and then if you take a generator like here on the torus, and then take their cup product, then that's going to give you the top cohomology class, whereas on the other guy, that won't happen if you take the cup product of the two little circles. And so that tells you that the two spaces aren't equivalent. The next example, which I labeled 3 for some reason, is about the linking of two links. And the idea here is that if you have two links and you want to know, or two rings, and you want to know whether or not they're linked, you can look at their cup product, and the linking number is actually basically fully recovered by their cup product after doing some games with duality theorems and stuff that is a bit too nitty-gritty and probably would deserve its own talk. And then finally, imagine that I put a picture of the complex projective plane here. The cup product can show you like when a certain map can't exist and stuff like this. Those of you who recognize this problem probably recognize it from a topology qualifying exam that I ripped because it was the first thing I thought of when making this slide. Okay, and then finally, when you need nothing to tell you something. The purpose of this talk is to show you that even when you think you don't have enough information, just like in the original case where you thought your cohomology groups couldn't distinguish the two spaces, you actually can dig a little deeper and find something new to tell you just a little more information, right? And so in this case of the Borromean rings, what's going on is each of these rings, if you sort of pay attention to it, none of them link with the other. Like if I deleted any one of the rings, the other two would be completely separable, and yet the 3 rings are linked. And this is the first casualty of my illness, is that I had a yarn Borromean rings made for you all, but it is stuck in the office, and I didn't want to like go to the office and get anyone sick. So tragically, you'll have to, actually I'll add it. Exercise, buy yarn and make rings. That's an important one for sure. Okay. And so you can ask, should we use some sort of geometric technique or think about an embedding or maybe even try to use some calculus? And the answer is that would totally work and would honestly be a little less contrived. But on the flip side, it requires doing calculus, which I don't want to do. And as an algebraic topologist, I firmly believe that we should be able to find an algebraic answer to this problem. And that's where the next part of the talk comes in. And so I really hope that I've convinced everyone that this is like some interesting idea, because I'm going to have to spend that goodwill on a few definitions now. Okay, so the first definition is that of a differential graded algebra. There's a lot of words on the screen. If you don't want to read them all, the idea is you have a chain complex and you have a product where if I take something in like the nth chain complex module and the mth chain complex module and multiply them, it should give me something in the n plus mth. And so it's like a graded multiplication. And the third axiom requires that like when I take the differential of a product, I get something that looks a little bit like the product rule from calculus. It's often referred to as the Leibniz rule. And so again, conditions 1 and 2 just tell you that we've got a cohomologically graded chain complex. So the degrees are going up 1 when I take my differential. And then condition 3 ensures that we're going to have a product when we take cohomology. And so, as I alluded to, if we have a differential graded algebra, we can take the kernel of the differential, mod out by the image of the differential, and get your classical notion of cohomology here. And it's a theorem that the product that I gave you in the differential graded algebra will still be a product in a cohomology, because when you sort of try to work everything out, you get some like error terms that don't quite give you what you think. But then it turns out that those are all boundaries or something, and then all of it vanishes mod the image of di minus 1. And so that's where that third axiom is exactly designed to make that work. And that's what it's there for. Okay. And so the classical example is singular cohomology. And I have a quick review for that for anyone who doesn't quite remember it. The idea is you take a simplex, which is basically just a triangle, a tetrahedron, a line or a point, or a higher tetrahedron. You take the continuous maps from that simplex into your space. You make a vector space out of it by just like asserting that it's a basis and taking the formal thing. And then you just take its dual. So you take maps from your freely generated vector space into Z over 2. And so that gives you a new chain complex. It's not hard to show that you can get a new differential out of it just by precomposing. And of course, this is the sort of biggest example of a differential graded algebra and sort of why people thought this generalization was a reasonable thing. And so if you want to, for basically the rest of the talk all the way until almost the end, you can assume that everything I'm thinking about is sort of the cohomology of a space. And in general, I think I actually do work in the cohomology of a space. And then to get a little more abstract, if I take any, oh, that F is supposed to be R. It works with R. Let's just fix that. Glad I chose F. That was easy to fix. Right. So if you have a commutative ring with unit, you can create a differential graded algebra in the way that I've sort of written down below. And this is actually very similar to slightly more complicated constructions called the bar and the co-bar complex, which show a lot in work that I care about. And if you like, computing derived functors and stuff, sometimes that's the way you choose to do so. It's not the most efficient way because it's very large, but that actually comes up. Okay. And then the last example, which I don't expect anyone to really be particularly familiar with, but a lot of times when we want to use Massey products, the real reason we want to do it is to make life in a spectral sequence a little bit easier, because computing differentials in a spectral sequence is hard. But if you can show that something's like a product, then you can kind of compute the differential based on like smaller, more atomic elements. And it turns out with a Massey product, you can actually do a similar thing, which allows you to like compute more differentials more easily is the pitch. but it works, and up to changing definitions to account for like bi-grading or tri-grading or whatever, everything is sort of the exact same. And why do we need this formalism? To be exact, we want to take cohomology, which is why we need something that's like a chain complex. We need cohomology in order to have witnesses, which is sort of how we're going to make something out of nothing. And then we need multiplication in order to use these witnesses and actually to get more of them and be able to name them easily and stuff like this. Okay. Are there any questions so far? I should say that if anyone has a question, feel free to message in the chat or to just interrupt me. I'm reading both. Question? Thought I heard a microphone. All right. Okay. And now we're going to talk about the philosophy of witnesses. And this is not really a mathematical thing. It's more like how we're going to think about the chain complex in relation to its cohomology. And the idea here is that normally you think of cohomology as a way of studying your chain complex, or the chain complex is just sort of some intermediary step between what you really want. But our idea is that the chain complex remembers things that the cohomology doesn't. And so maybe we might be able to leverage the fact that cohomology kills stuff in order to get more stuff out of it. And so to be explicit, if we think about cohomology, that's just, you have a sort of kernel of a boundary over the image of a boundary. And inside of the chain complex, you have just the kernel, and it sort of projects onto this when you take the quotient. And so if I have some element in cohomology called A, then a representative for A is just some preimage under this map. And so in particular, choosing such a preimage does require a real choice, and there might be, you know, any number of preimages. I mean, the singular complex is massive, and yet cohomology is normally like small, generated by one or two elements, so you expect like a lot of possible choices. Then if A is 0, then a representative for the fact that A is 0 is if A bar here is not 0. So A bar is killed by taking the quotient by the image, which means that sort of A bar is equal to some dx, where d is the boundary map that's generating that image, right? And so the fact that A bar is equal to dx witnesses the fact that A bar is going to be killed when we switch to cohomology. So just to repeat, you have something in the kernel, you have something right here, and that thing is not necessarily 0, but then you take a quotient and suddenly it's 0, right? And in fact, the quotient is from the image of some other map, which means that A has to get, or A bar has to get hit by something in order to become 0. That's the philosophy. And if you want to remember it in one sentence, cohomology kills a bunch of classes. For example, you go from the singular complex to like a 1 or 2 generator cohomology group. And witnesses tell you when things get killed. That is the cute pitch. And so a quick example before I pause for some more questions. All of these spaces are contractible and they have the same cohomology in H1. But let's think sort of about what's going on exactly. At this point, let me switch to my laser. At this point, there's not a lot going on at H1. In fact, there are no 1 simplices, so it's immediate that that cohomology group is 0. In this one, there is a 1 simplex. It's just the line. However, it doesn't form a cycle, so it had no hope of ever generating a class in cohomology. On the other hand, if I name these guys A, B, and C, and this guy X, then A plus B plus C, mod 2, could be a generator for cohomology. And so it's not necessarily trivial. The only reason we know that it's 0 is the fact that dx is going to be A plus B plus C. So the fact that this is equal to dx tells us that this filled in part witnesses the death of A plus B plus C. And so that's sort of telling you that something is 0, but cohomology doesn't know the difference between which situation we're in. So it's really the chain complex that can remind us like, hey, maybe this thing is 0, but there's a reason for it, and that is extra information that you're losing. All right, and now we're going to talk about the Massey product. And in particular, we need 3 classes in order to define it. So A, B, and C. And they can be in totally different gradings. So A can be in dimension 1, B can be in dimension 3, et cetera, et cetera. And we're also going to pick representatives for them in the chain complex. The other requirement is that A, B, and BC both have to be 0. So A, B, and BC both have to be killed. If you remember what I said earlier, I said that we're going to be using the multiplication to both like use and find witnesses. And so the idea here is that we're not looking for a witness that 0 is killed. We're looking for a witness that a product is killed, basically. And then we're going to assume that we have chosen witnesses X bar and Y bar, and I'll talk about whether or not that choice matters in a bit. Then we're going to define a class called A tilde, which is given by this. And if you think that this kind of looks strange, one way to make sense of it is that X and AB are related and Y and BC are related. And so A tilde is sort of just like ABC plus ABC. It's not actually that, because that would be 0 mod 2, and we don't want it to be trivial. But that is the intuition that helps me remember which way to write it. Okay, are there any questions about this setup?
Yeah, so very small thing. Is this cup product or product that's going on here, is it a commutative?
No, it is not in general commutative. And in fact, we're going to have an example later where it isn't commutative. A good point.
Cool.
Any other questions? All right. Okay, and then the result that's going to basically help us bootstrap is this A tilde is a cycle, meaning that D of A tilde is 0, meaning it could possibly be a non-trivial element in homology. And so, or cohomology. So what we've done is we've taken the fact that AB is 0 and BC is 0, and we've somehow managed to lift that up to something non-trivial, which is sort of the philosophy that I've been trying to push, where it seems like we, hope is maybe lost, or that information isn't able to be obtained from these classes, but in fact, you can actually get more out of the fact that they're trivial. And then this is actually a really good exercise. I do recommend people think about this, is that everything I've said is only true up to the fact that 1 and -1 are the same. And so in particular, there is a definition of A bar where you use a sign like -1 to some power, and that makes all of this work without taking mod 2. So this would be a minus. Maybe as a hint, the -1 goes here. So it's right before the AY. Okay. And now, of course, we are going to wonder about the choices we've made, right? So first, just notice that we can easily figure out the degrees of X and Y. Basically, AB is in degree NA plus NB, and then DX is equal to AB. I should be using these bars. DX is equal to AB, and so you can downshift. You take down 1 degree because the differential is lifting things up a degree. So in order for DX to hit AB, DX has to live 1 degree below AB. Same thing for Y. And then this product, you just read off the degrees, because the degree of a product is the sum of the degrees, and you get NA plus NB plus NC minus 1. And then when it is defined, A tilde has given us some sort of class in this cohomology group. And it's worth pointing out, right, that the intuition I gave earlier is that it's kind of like ABC plus ABC, but both of these would live in 1 degree higher. It would just live in NA plus NB plus NC, meaning that we sort of have genuinely gotten something that is different, even though it kind of feels like we're just playing a trick. Any questions about this? Okay. And now what you really wanted me to say is that the choice of X bar and Y bar don't matter. But unfortunately, this is the one time in topology where, or I guess twice, since I'm going to do it later today too. It's one of the 2 times in topology where I have to tell you that these choices do matter. And in fact, this is a huge issue to working with Massey products, is that depending on your choices, you can get different answers. which means that a lot of things that like you expect to be like algebraic identities and stuff are like subsets and weird indeterminacy. And so that is sort of why they're not like as ubiquitous as the cup product, is they take a lot more work to sort of think about and work with.
Wait, okay, so another possible dumb question. What is the difference between the Massey product and the cup product? For some reason, I thought they were the same thing up to this point, or I did not.
So the cup product is just like, if I have two cohomology classes, A and B, I can multiply them. Maybe the easiest way to give the definition is just like, you're working in the cochain complex. And so A and B are actually maps into Z2. Z2 is a ring. And so you can multiply maps into a ring, except that there's like a slight adjustment here, because what you're really doing is like, you're breaking up a simplex and then multiplying it. But anyway, that's just a product that comes for free with a space. And then the Massey product is defined when like AB is 0, meaning that it like that product induces the 0 map or is cohomologous to the 0 map. And BC is 0, meaning the same thing. And now suddenly I can give you a product of 3 elements that isn't the same as their like the Massey product is not the same thing as like ABC or any scalar of it.
I see.
So this is like a genuinely different product.
If it helps,
I
Sam,
haven't even defined this notation yet. This is the Massey product. I'll define it in a second.
if it helps, Sam, the juxtapositions, basically all the juxtapositions above are cup products, and then that A tilde.
Okay, yes, that was, I guess,
is the the Massey product. There you go.
Right.
Thank you.
Yes, so the Massey product is the set of all possible classes A tilde as we vary the choices of X bar and Y bar. And you might ask, like, can you tell me how different two Massey product things can be? And that's where the indeterminacy of the Massey product comes in. So the indeterminacy is just defined to be like the difference of all like two, like you pick any pair of elements in the Massey product set, and then you subtract them and you ask like, where does that difference live? How close is it to 0? Because if the indeterminacy was all 0, then you would actually have a well-defined class. So the size of this guy sort of tells you how much information is sort of here, but also like how unwieldy it is, because the more different classes it contains, the less it can really know, right? Because all those classes are different and they could act differently. And so you don't really expect a lot of identities to hold if like there's a ton of independent elements all called the same thing, right? Right, and so the Massey product, the difference between them, oh, I messed up my slides here. I'm going to give you the actual explanation, but the idea is that the Massey product is a sort of well-defined function, but you have to make the domain this like set of pairs where AB and BC vanish at the same time. I mean, it's important that AB and BC are vanished, right? You can't just take like AB0 and CD0 and like make a Massey product. You need 3 things. And so the indeterminacy can be described explicitly. And the idea is, right, that the definition of X bar and Y bar is that X bar is equal to AB. And so if there was some other choice like X prime, such that it also is equal to AB, then we know that dx minus X prime, I'm getting lazy with my bars here, dx minus X prime has to be 0, which means that our choice has to be well-defined up to some like cycle in cohomology, or just cycle in general, right? Whatever the difference between our two options is, it has to be 0 under the differential. And if you work it out in full detail, you see that the indeterminacy is actually given by this like sum of cosets, which is why I say that the image is well-defined up to a double coset. And so the idea here is that like this homology group and this homology group are really what determine how much variance there can be in a Massey product. So for example, like suppose you knew that everything here was like killed by A, like A times anything is 0, then this indeterminacy would just vanish. And suppose you knew that anything times C was 0, then this one would also vanish and you'd have a well-defined product. And so that's sort of how like the cup product controls how much indeterminacy there is. So like if you're working in a space where there is no cup products at all, like the Borromean rings, then there is going to be no indeterminacy at all. Are there any questions about this? Because I think this is one of the trickier aspects compared to like other cohomology things. All right. All right. So the example that I really wanted to work out for you all was to prove that the Borromean rings were linked using Massey products. It turns out this takes like many pages of math and was a lot harder than I thought it was. And so the moral of this story is that even if you are pretty sure you could learn something if you just read it carefully, that doesn't mean that you're right. But this is actually a very cool story, and I do plan to read it in detail later and understand better why it's true. And if you would also like to understand it, you can find a reference here. Oh, I just saw your question, Nathan. Sorry. So the reason why this is NA minus NB minus 1Z is that like basically X lives in that degree in the chain complex. Like X lives in NA minus NB minus 1 because, oh, that actually probably should be addition. Okay, there we go. Now I fixed it. Thanks for pointing that out, Nathan. I'm glad that I fixed it. Right, okay. So again, the Borromean rings, if you take the Massey product of those three rings, you will get something non-trivial. And it ends up being basically equivalent to something called, I think like the Milnor mu bar invariance, if you're familiar with them. But yeah, so it can tell that they're linked, but working through it is very painful. And so I used Stack Exchange to find a much more tractable example. It's actually surprisingly hard to come up with one because I'll actually give some intuition why later. Okay. And so this is just a simplicial complex. One thing in particular to note is that all of these are identified, but I didn't write it. So all those points are identified, all the things with the same label are identified. It's kind of small, but everything is oriented and everything gets a total ordering. And so this is a bona fide simplicial complex. And we're going to just very quickly compute its cohomology, cup products, and find a non-trivial Massey product living inside of here. All right, and then thank you to this Math Stack Exchange user for coming up with this in answer to his own question. Okay. So first we're going to compute the cohomology. There actually is a quick trick to this, which I thought I might explain, which is the differential on a dual. You basically just write down everything that it's a boundary of. So A is a boundary of capital A, it's a boundary of capital C, of capital B, and capital D. So you just write all those. B, for example, is only a boundary of capital A and capital D, so you just write down those, et cetera, et cetera. The only sort of difference being that it's actually like up to a parity. So if I had something like this, then that would be 0 for A because A shows up twice. And then this all changes a good deal if you, it would look like, I think, a cone to those who are interested, depending on how I orient them, I guess. It could also look kind of like a Mobius strip. Anyway, like a cap, actually. Anyway, yeah, so this is how you compute all these differentials. It's also why I think that computing cohomology stuff over F2 is like the best way to get geometric intuition. And you can sort of write down that this is sort of the result you get, right? And so the first one is, it's connected, so you should just sort of expect that. The second one comes from the fact that this differential is completely 0. And then if you want to think about it, there are two different ways to get A, B, C, and D. You can add B star to E star, or you can add C star to F star, and that will both get you A. And those two classes are going to generate the kernel when you like add them to A. So in particular, the kernel is going to be generated by these guys. So this says that A star, which is A plus B plus C plus D, is equal to C star and F star, which are like A plus B and C plus D. And then these are just two different ways to like write down A plus B plus C plus D or something. I think I bracketed them incorrectly. But anyway, that's where these classes come from. And while they look a little contrived, it's because I'm going to use them to find the Massey product. So remembering that this is alpha and this is beta is important. And so the cup product also has a trick mod too with this simplicial complex thing. Basically, a cup product is non-trivial if like I can find an oriented corner that looks like this. So C star A star is going to be non-trivial and it's going to give you capital A star. F star A star is going to be non-trivial and it's going to give you capital C star. But it does have to be oriented and it does have to be in that configuration. And if you work all these out, the only products on the generators are these four, and things do not commute like Sam alluded to earlier. So like it doesn't count here, right? This doesn't count as a to C, it's only a C to A because of the orientation I chose. Right. So this gives you all the non-trivial cup products. And then finally, we can compute our Massey product using all this information. Let me try to fit it all on screen. There we go. Then alpha squared is going to be given by this, which is killed by a witness, E star plus F star. Alpha beta is going to be killed by this witness. And you can sort of just write this down and like do it all out. There's no like tricks involved. It's just working with the algebra and then remembering this is what the products all are. And so these guys go to 0, which means that this Massey product is well defined, alpha, alpha, and beta, because alpha squared is 0 and alpha beta is 0. And I never said that the 3 classes had to be different. And we can prove that this is non-trivial. So maybe this is like a hint as to why working with Massey products can be a bit of a pain, because computing these cup products took us like a minute for 5 of them. And then computing this Massey product took all of that time plus everything else. And you might ask, Max, why is this example so contrived? Why couldn't you like give us a space that we know and love? And the reason is that Massey products mostly show up in chain complexes where like everything is massive, right? So much stuff is getting killed that it's not hard to find 2 classes so that their product is killed by something else. And it's just like there's a lot of interactions going on. And so it's sort of, at one sense, a bit more chaotic, but on the other hand, it's actually a lot more simple to find a Massey product because you just sort of like try things and are more likely to get something. Whereas for most manifolds and stuff, you're going to see trivial Massey products. There's also some notion called a formal manifold by Sullivan. And apparently this is like the requirement for all Massey products on a manifold to vanish and stuff like that. So if you're familiar, feel free to email me and explain it after this. But the real issue here is that spectral sequences are massive, especially E1 of most spectral sequences, the first page. That's where a bunch of Massey products show up, and that's where they show up in the things that I mostly like think about and work on maybe. But first, I want to do what I promised earlier and talk about a higher product in homotopy. Are there any remaining confusions about the Massey product before I move on to the bendy version? Okay, great.
Hey, question.
Yeah.
How do you know that that Massey product that you computed is well defined? Because didn't it depend on the choice of the witnesses?
Right. So I'm technically being a bit of a cheater here, and what I should really write with what I've proven is this. And then what you'd want to do is look at the indeterminacy I gave earlier, and hopefully that's 0. I didn't actually think about it, but it might be. So many of these cup products die that I wouldn't be totally surprised either way. But basically I've shown that there is a non-trivial element, not that it is this non-trivial element. But a lot of times that's actually good enough. But yeah, that's a great question.
Okay, thanks. And then just very quickly, like, I don't know if you said this already, but like, what is the like geometric significance of having a non-zero element that is a Massey product?
Right. And so that's part of why it's so hard to like define this. Is in the Borromean rings one, you can sort of get some intuition for that. It's sort of like there are 3 things that are connected in a way that the cup product can't see but should be able to, kind of. But in general, I don't personally have a ton of geometric intuition for it. Maybe the next part of the talk, which talks about the homotopical triple product, will like make you believe that there is some to be had, though.
Okay, thanks.
Yeah,
Just as a guess, I would imagine that the way to understand the geometric intuition, Max, is to, you said there's a calculus proof of this Borromean ring thing.
Yeah,
and you should be able to reword that proof in terms of the topological objects that you've defined, and that should tell you what the actual goal of this object is to measure.
Yeah, and there is actually in Massey's product higher order linking numbers. That does show up, and it does explicitly relate it. So if you're interested, it is a great paper to read.
Nice.
And I would be happy to read it with someone because there's a lot of details. Okay.
Can I ask one?
Yeah.
Sorry, just one more really quick. For the Borromean rings example, what space actually are we computing the Massey product on? Is it like the complement of the rings?
So what you're doing is you're taking the complement of the rings via Alexander duality in S3, and then you're doing Lefschetz duality to get, because that gives you homology, and then you do another form of duality in order to get a new cohomology theory that is closely related, and then you like translate between those two worlds to get your answer.
Got it. Okay, thanks.
Yeah, no problem. Okay. And so a quick review of some constructions in topology. I'm gonna have to write here, so I'm gonna move this into my lap. The first is that if this is a space, I can tell you that its cylinder is it times the unit interval, which just literally looks like a cylinder if you draw all spaces as disks. Its cone is you just collapse that top part. So you get like this. So what I've done here is I've just like squished that to a point. And then you can get the suspension by sort of doing this and squishing both copies to a point. The unreduced suspension is maybe what a topologist would call it. These are going to be important. Gave myself more space to draw, never mind. Okay, and now this is a little trickier, right? So if I have a homotopy between two maps, FG, X to Y, and I know that F is homotopy equivalent to G, then what that's really saying is that I have a map from the cylinder on X into Y. That is, if you restrict to the top cell, G, and if you restrict to the bottom, you get F. And that's sort of what the homotopy is telling you geometrically. In particular, suppose I know that G is actually just like a 1-point constant map. So I know that F is null homotopic. Then the top is actually going to just sort of look like this once I've taken the quotient. And so a null homotopy of F is the same thing as an extension to the cone, which means that like, if I have a map that contracts F all the way to the top, then that means I could just squish the top anyway because it's a point. And now I have a map for my cone. And then finally, this is an important theorem in algebraic topology, which says that the suspension is just two cones glued together. And if you look at it, you can see the proof. And so the thing I want to add is that if I have two different null homotopies, or if I have like two maps from a cone that agree on the same space, like they're the same at the base level, then that means I can just like do the top null homotopy on the first part of the suspension and do the bottom null homotopy on the bottom part of the suspension. And that gives me a new map. And because cones are null homotopic, you can contract a cone, but suspensions aren't in general. And so this actually gives you a new potentially non-trivial map, which should sound like something I said a little earlier. I'll give myself more room to draw. Right. So suppose I have exactly what I told you that I wanted to have. I have a map F from X into Y. Actually, I need more than this. Suppose I have three maps from X0 into X1, into X2, into X3, and I'll call this alpha, beta, and gamma. And suppose I know that alpha beta is null homotopic, or I'm giving away the punchline. Suppose I know that beta composed with alpha is null homotopic, and I know that gamma composed with beta is null homotopic. Then that can be realized as two null homotopies. Basically, the first one is sort of like x0 cross I into x2. And the second is x1 cross I into x3. And so the final ingredient I need is that if I have a map alpha from x0 into x1, then I can extend it to their cones by just doing alpha at every layer and then sending the point to the point. And that'll be a continuous map, and it shows that taking cones is actually a functor. But anyway, I can take the cone of a map. And so my final construction for you today is going to be as follows. I start with the suspension on x0. I map it into the cone on x1. I map into, I map into x2, and then I map into x3. And so what we're going to do is on the top part of the cone, we're going to do the cone of the map alpha. So this is just the original map, but we've extended it. On this guy, we're going to do the first null homotopy of the null homotopy of beta circ alpha. And then here, we're going to add the null homotopy of beta circ gamma, or I think this is gamma circ beta. Yes, this is gamma circ beta. And then this is gamma. And so in particular, all of these maps agree on this little medium part. It's just that they extend differently to the different cones. And so in particular, I've given you a map from the suspension of x0, that's the symbol for suspension, into x3. Are there any questions on this picture?
What's the map from the cone of x1 to x2?
The cone of x1 to x2, this is just beta.
Okay.
And so the idea here is that like at every bottom level, you're looking at the exact same map. But on this first section, you're taking the cone of alpha composed with the null homotopy of gamma circ beta. And on the bottom part, you're taking the null homotopy of beta circ alpha composed with gamma. And so this kind of looks like if I label this H2, and if I label this H1, this looks like sort of H1 circ alpha union gamma circ H2, modulo me writing function composition in the right order.
So just to clarify, beta is not defined on the whole cone.
Beta is not, beta could be, but it doesn't need to be. Like beta is only defined on x1.
Okay, cool. So yeah, I'm just checking that map is like a partially defined map.
Yeah.
Okay, cool. Then it makes sense.
Right. And so the idea here is that this looks very similar to the Massey product. And my goal is to convince you that it basically is. And so we write alpha, beta, gamma for surprise, surprise, your choice of null homotopy matters. So this is really a set of maps, and it's given by the union of these two maps that we've constructed. So for example, this is well defined up to homotopy. So if I have a bunch of spheres, then this is going to be just a bunch of elements in homotopy. Find more and more elements in the homotopy groups of spheres.
Max, we had a freeze for about the last 7 or 10 seconds.
Oh.
So say whatever you just said again.
Right. So what I'm saying is that if all 4 of my spaces are taken to be spheres, then all of this is just like elements of homotopy groups of spheres up to homotopy, right? And so what ends up happening is you get sort of new elements for free out of old elements just by taking their tota brackets and like lifting them up to different classes. So in particular, you do need to know that alpha and beta compose to 0 and beta and gamma compose to 0, but that actually does happen surprisingly often. For example, it's an important theorem. There are maps that are similar to the Hopf map, if you're familiar. And the Hopf maps in stable homotopy completely generate the stable homotopy ring of spheres under tota brackets. which is surprising because we also have like very so the main example that I've shown you so far is actually not that helpful. But what I want to convince you of is that the sort of Toda brackets of spheres that I talked about and the sort of Massey products in cohomology can be related really closely by the fact that the atom spectral sequence can converge to the stable homotopy groups of spheres. So in particular, you have homological data on this side, homotopy data on this side, and in some sense, you want Massey products to be able to turn into Toda brackets and to be able to detect things in both directions. And my punchline is that if you ignore all the technical conditions that make this not true, then you can compute Massey products to some extent. There's actually computerized versions of it in the atom spectral sequence. The Massey products in the atom spectral sequence can be used to compute differentials. And the Masseys in the atom spectral sequence detect the Toda brackets in the homotopy groups of spheres. And these three facts had a huge influence on the early theory and continue to be important today. And then this harder exercise, which you can actually take a little bit longer than tomorrow to turn in, but just make sure that I'm the only person you show it to. All right. And that is all I really planned. My other thing is that I want to shout out that if you want to understand the last like 2 slides of this talk, you should come to these seminars on Tuesdays at 10:30 a.m. where some of your classmates will be speaking from November 2nd to November 30th. And I'll be speaking on the 23rd about the atom spectral sequence. But yeah.
Nice plug on that last one. All right, everyone, let us thank the speaker. Any questions?
I have a question. So it's kind of, if you look at like some algebraic, some cohomology theories in algebraic geometry, some of these higher arity operations probably should exist, right? But I don't know that I've ever really seen them. Do you have any idea if there's a reference for them or if they've been looked into much?
I don't have a reference in mind or anything, but I can maybe give a hint as to why they aren't super ubiquitous. And I think it's because, and I mean, I could totally be wrong here, but my understanding is that a lot of spectral sequences in algebraic geometry, like everyone hopes they collapse very quickly, and they normally do, which means that like you don't get a ton of higher differentials, which means that going through all the pain and effort of computing Massey products just isn't super worth it most of the time. But they should exist in theory. And in fact, you can give far more general definitions of certain things that I talked about today. So I'm sure there must be a reference. I might be able to look for one and email if it comes up.
Actually, did you say earlier that the Massey products, a lot of Massey products on manifolds end up being 0?
Yeah, on
maybe that's the
manifolds. And I couldn't find any like you sort of expect when you Google Massey product examples for like a manifold to show up, and I couldn't find a single one. That might be my Googling skills, but I think that they don't show up a ton in like nice spaces for some reason. I think especially when it's easy to name generators and like you get small chain complexes as a result, you're unlikely to support them.
Interesting. Any additional questions or follow-up questions? This is an annoying one, but just to double check, it's been a while since I've thought of differential graded algebras, but so we kind of said at the beginning that we're just working at over Z mod 2Z, but then you made some definitions that were valid in a more general setting. In my memory of the general setting, you have that product rule is graded.
Yes, yeah.
So you that is correct. Like you will have these. Okay, cool.
It should be like -1 to the product of the degrees of the two classes or something like this.
Whatever it is for differential forms is whatever.
Yeah.
Okay.
So yeah, that's totally correct. I just didn't want to write it. And the same thing in the Massey product that ends up showing up In the differential that I talked about for the like tensor complex earlier, that also should be apparent, I believe. So yeah, in most of these places where you would expect like a causal sine rule, you do have one.
Cool.